At 3:47 a.m. on November 12th, every atomic clock on Earth stuttered. Not by seconds, not by milliseconds, by exactly 3 nanoseconds, 3 billionths of a second. A deviation so microscopic it should be impossible to detect, let alone explain. But you're about to discover why this tiny shift sent classified briefings to 12 governments, locked down intelligence communities worldwide, and forced 400 laboratories to question everything we know about physics. Because something entered our solar system, something moving at 87 kilometers per second, something so dense it bent space-time itself. Its designation 3I/Atlas, the third confirmed interstellar object ever detected. And unlike the mysterious Oumuamua that vanished before we could study it, this one left evidence. Hard, measurable, undeniable evidence. Evidence that's still being analysed in classified facilities right now. You're not supposed to know this yet. But in the next 72 hours, before 3I/Atlas exits our measurement range forever, you're going to learn what really happened when an object from beyond our solar system changed time itself. If you find yourself hooked by what you're about to discover, that's exactly when you should hit that subscribe button and ring the notification bell. Not because I'm asking, but because you genuinely want more stories like this. Drop a like if the science genuinely fascinates you, and comment where you're watching from. I actually read every single one. Now, let's dive into what happened on day 1. You're sitting in the control room at the National Institute of Standards and Technology in Boulder, Colorado. It's 3:47 a.m. and you're 3 hours into your overnight shift monitoring the NIST F2 cesium fountain atomic clock, one of the most precise timekeeping devices humanity has ever built. Your coffee's gone cold, your eyes are heavy, and then, on your screen, you see something that shouldn't exist. The readout flickers. Just for a moment. 3 nanoseconds. Your first thought, instrument error. Your second thought, someone spilled coffee on the equipment. But here's what makes your blood run cold at that exact same moment. 947 miles away in Braunschweig, Germany, the Physikalisch-Technische Bundesanstalt's atomic clock registers the identical anomaly. Then Paris, then Tokyo, then Beijing. Within 90 seconds, 437 atomic clocks across 6 continents report the same impossible deviation. 3 nanoseconds doesn't sound like much, does it? It's the time it takes light to travel about 3 feet. If you tried to experience 3 nanoseconds, you couldn't. Human perception operates at roughly 13 milliseconds, which makes 3 nanoseconds about 4.3 million times faster than you can blink. But here's why it matters. Modern atomic clocks are so precise they can detect time dilation, caused by raising the clock just 2 centimeters higher off the ground. Einstein was right. Gravity does warp space-time, and we can measure it. These clocks don't just tell time, they feel the curvature of reality itself. So when 437 of them stutter simultaneously, you're not looking at a malfunction, you're looking at something massive enough to bend space-time across the entire planet. You grab your phone, your hands shaking slightly as you pull up the emergency protocol checklist that you've never actually had to use in 7 years on the job. Section 4.7 Anomalous Gravitational Events. You've always thought this section was theoretical, something the bureaucrats added to look thorough. Now you're reading it word for word, and every sentence feels surreal. Contact NASA Planetary Defense Coordination Office. Priority immediate. The call connects on the first ring. That's your first clue this isn't just your problem anymore. The voice on the other end doesn't ask who you are. Doesn't ask for credentials. Just says which facility, you tell them Boulder. There's a pause. Then, we've got eyes on it. Stay on your station. Do not discuss this externally. You'll receive a classified briefing packet within the hour. The line goes dead. You sit there, staring at your monitor. where the atomic clock has already restabilized. The deviation lasted exactly 11.3 seconds from start to finish, the time it took for the gravitational wave to wash over Earth and dissipate. You start doing mental math. To cause detectable time dilation globally, an object would need either tremendous mass concentrated in a small volume, or it would need to be moving at a significant fraction of light speed, or both. Your mind goes to black holes, but that's impossible. A black hole close enough to affect our clocks would be tearing the solar system apart. Neutron stars, same problem. The classified email arrives at 4:23 a.m. The subject line reads Confidential Interstellar Object 3, I/Atlas Initial Detection Report. Your security clearance barely gets you past the first page, but what you can read changes everything. The object was first detected 47 hours ago by the Asteroid Terrestrial Impact Last Alert System in Hawaii, the same network that's supposed to give us warning about killer asteroids. But this wasn't an asteroid. Initial spectroscopy showed a velocity of 87.3 kilometers per second relative to the Sun. For context, Voyager 1, humanity's fastest spacecraft, moves at 17 kilometers per second. The average asteroid in our solar system about 25 kilometers per second. This thing was moving more than 3 times faster than anything gravitationally bound to our Sun should move. That velocity told astronomers something profound. This object didn't originate here. It came from interstellar space. You keep reading. The object's trajectory entered our solar system at an 87-degree angle to the ecliptic plane, the flat disk where all our planets orbit. Imagine a dinner plate representing our solar system, with the Sun in the middle and planets going around in neat circles. Now imagine something diving almost straight down through that plate like a knife. That's 3I/Atlas. Natural objects in our solar system don't do this. Their orbits are tilted. Sure, but rarely more than 30 degrees. An 87-degree angle screams outsider. You scroll to the section marked Mass Estimation Preliminary. And this is where things get weird. Based on the gravitational perturbation measured by your atomic clocks and 436 others, combined with optical observations estimating the object's size at roughly 340 meters in diameter, the physics team calculated its density. You read the number twice, then 3 times, 22.4 grams per cubic centimeter. Let me put that in perspective for you. Iron, the stuff that makes up most of Earth's core, has a density of 7.8 grams per cubic centimeter. Lead 11.3, gold 19.3. Osmium, the densest naturally occurring element on Earth, clocks in at 22.59 grams per cubic centimeter. This object is denser than everything in the solar system except osmium, and it's doing 87 kilometers per second through space like it's late for an appointment. You lean back in your chair. The coffee's definitely cold now, but you take a sip anyway. Your brain's racing through possibilities. Could it be a solid osmium asteroid? Theoretically possible. But osmium is incredibly rare. We're talking about finding a 340-meter sphere of the rarest stable element, somehow ejected from another star system, somehow surviving the journey through interstellar space for potentially millions of years. The odds make winning the lottery look like a sure bet. The report includes a quote from Dr. Avi Loeb, the Harvard astronomer who's been arguing for years that we're not paying enough attention to interstellar objects. He's on record saying about Oumuamua, the first confirmed interstellar visitor in 2017. The excess acceleration of Oumuamua was not typical of comets, and its shape was not typical of asteroids. When you have an object that doesn't fit natural explanations, you have to consider artificial ones. You remember the controversy that statement caused. Scientists don't usually throw around the word artificial unless they're talking about satellites or space probes. But here's what makes 3I/Atlas different from Oumuamua. We caught it earlier. We have better equipment. And most importantly, it left physical evidence we can measure that 3 nanosecond signature on every atomic clock on Earth. At 5:17 a.m, your supervisor walks into the control room. She's not supposed to be here. Her shift doesn't start until 8 a.m. She's carrying 2 fresh coffees and a folder with a red stripe across the top. Red stripe means need to know classification. She hands you one of the coffees and sits down. You saw it. She says, not a question. You nod. Here's what they're not putting in the preliminary report. She continues, opening the folder. The European Space Agency's Gaia satellite measured a microgravitational lens effect as the object passed behind a distant star cluster. They're running the numbers now, but early estimates suggest the object's gravitational field is consistent with its observed mass. That rules out hollow structures. Whatever this thing is, it's solid all the way through. But that density, you start. I know. She cuts you off. That's why NASA's convening an emergency session with the International Astronomical Union. They're calling in planetary scientists, astrophysicists, materials engineers, even a few people from Los Alamos National Laboratory. Why Los Alamos, you ask? That's the nuclear weapons lab. She looks at you for a long moment. Because the only materials we know of that can achieve that density are either naturally occurring osmium-iridium alloys from asteroid impacts, or certain compressed materials that exist only in laboratory conditions, or inside nuclear weapons cores. The implication hangs in the air like smoke. Your mind jumps to the obvious question, could this be artificial? Could someone or something have sent this? But before you can ask, she closes the folder. Your job right now is to monitor for any secondary effects. Keep logging the data. The next 68 hours are critical. That's how long we have before it exits our effective measurement range and disappears back into interstellar space forever. She stands to leave, then pauses at the door. And one more thing. In 1908, something exploded over Tunguska, Siberia, with a force of 15 megatons, 1,000 times more powerful than Hiroshima, flattened 80 million trees across 830 square miles. We never found an impact crater, never found fragments, for over a century. We've assumed it was a small asteroid or comet that disintegrated in the atmosphere. But what if we were wrong? What if it was moving too fast interstellar fast? What if we've been missing these objects all along because we didn't know what to look for? She walks out, leaving you alone with that thought and 437 atomic clocks that are all perfectly synchronized again, as if nothing ever happened. But something did happen. And as you sit there watching the sun start to rise over the Colorado Rockies, you realize that humanity just received a message. Not in radio waves or binary code, but in the language of gravity itself. 3 nanoseconds, the universe's way of tapping us on the shoulder and whispering, pay attention. The question now isn't whether we detected something impossible. The question is, what else have we been missing? And perhaps more unsettling, was this object's trajectory through our solar system random or deliberate? Because if you plot its course backward through space, accounting for galactic rotation and stellar drift, 3I/Atlas came from a very specific direction, a direction that happens to align with a star system 47 light-years away, a star system where, just last year, the James Webb Space Telescope detected atmospheric biosignatures on a potentially habitable exoplanet. But that's classified information. Information you definitely shouldn't know. Information that's about to become very, very relevant as we dig deeper into what 3I/Atlas really is, and what its arrival might mean for everything we thought we knew about our place in the universe. You're standing in the viewing gallery at CERN, the European Organisation for Nuclear Research, staring at the Large Hadron Collider control room through bulletproof glass. It's 9:34 a.m. Central European Time, 14 hours after the clock shift, You're not supposed to be here. But when Dr. Sarah Chen from the Particle Physics Division calls you at 6 a.m. and says, "I need you to see this in person," you get on a plane. Sarah's been studying atomic precision for 2 decades. She's the kind of scientist who gets excited about measurements so exact they make your head hurt. Right now, she's pointing at a screen displaying data that looks like abstract art waves and peaks and valleys in colours you didn't know monitors could produce. "These are cesium atoms," she says, her finger tracing a particular wave pattern. Cesium 133 to be specific. You want to know what makes atomic clocks tick? It's these little guys. A cesium atom oscillates, vibrates. If you want the simple version, exactly 9,192, 631, 770 times per second. Not approximately. Exactly. That number defines what we call 1 second. It's the universe's metronome. You nod, but honestly, you're still processing the fact that you flew across the Atlantic because of 3 nanoseconds. Here's what makes this beautiful, Sarah continues, warming to her subject. When you put cesium atoms in a specific energy state and hit them with microwaves at just the right frequency, they jump between energy levels. We measure those jumps. Every 9,192, 631, 770 jumps equals 1 second, as defined by international agreement since 1967. The NISTF 2 clock in Boulder where you work, it loses 1 second every 300 million years. The experimental strontium clock they're building, 1 second every 15 billion years longer than the universe has existed. Okay, you say slowly. So these clocks are ridiculously accurate. I get that. But how does that help us understand what happened with 3/Atlas? Sarah grins. Because atomic clocks don't just measure time. They measure space-time itself. She pulls up a new image of Einstein's face next to a diagram of Earth, with curved grid lines around it. You've heard of Einstein's general relativity. Right mass curves space-time. The more mass, the more curve. The more curve, the slower time moves. It's not theoretical anymore, it's measurable. GPS satellites have to account for this. They're moving fast and they're higher up where gravity is weaker, so time passes differently for them than for us on the ground. If we didn't correct for relativistic effects, your Google Maps would be off by about 6 miles per day. You've heard this before, but hearing it in the context of 3/Atlas makes it feel different, more immediate. Now, here's where it gets interesting, Sarah says, pulling up a 3-dimensional model. When 3/Atlas passed through our solar system, it created what we call a gravitational wake. Imagine dragging your hand through water. The water displaced by your hand creates ripples. Right, same concept, except instead of water, we're talking about the fabric of space-time itself. The model shows Earth as a blue sphere, with coloured lines representing space-time curvature. As a small red dot representing 3/Atlas moves past Earth, the lines warp and bend, creating a visible distortion that propagates outward. The object's mass compressed space-time as it passed, Sarah explains. For 11.3 seconds, every point on Earth experienced slightly stronger gravity, and in stronger gravity, time moves slower, 3 nanoseconds slower, to be exact. Every atomic clock on the planet felt it because they're sensitive enough to detect gravitational changes that would occur if you simply raise the clock by 2 centimeters. You stare at the simulation. So, the clocks didn't malfunction, what? They accurately measured a real change in space-time. Exactly. Sarah's eyes light up. This is what people don't understand about atomic clocks. They're not just timekeepers, they're gravitational field detectors. We've used them to measure the gravitational redshift effect by comparing clocks at different heights. We've detected the gravitational influence of the moon's tidal forces. Last year, a team at NIST detected gravitational effects from rearranging masses in the same room as the clock. But this This is the first time we've detected a gravitational signature from an interstellar object. She pulls up another dataset, this one showing overlapping wave patterns from different locations around the globe. Look at this. This is data from NIST in Boulder, PTB in Germany, BIPM in Paris, NMIJ in Japan, and NM in China. 5 different facilities, 5 different continents, 3 different clock technologies, cesium fountain, strontium lattice, and hydrogen maser. All of them detected the same 3 nanosecond deviation at the same moment. The probability of this being a coincidence or systematic error less than 1 in 10 billion. You lean closer to the screen. So what does the 3 nanosecond shift tell us about 3I/Atlas itself? Sarah sits down, and her expression becomes more serious. Here's where we need to do some physics. The amount of space-time curvature and therefore time dilation depends on 3 factors: the object's mass, its distance from us, and its velocity. We know its distance from orbital tracking data. We know its velocity from spectroscopy, so we can work backward to calculate its mass. She opens a calculator app and starts typing. The object passed at its closest approach approximately 0.84 astronomical units from Earth at about 78 million miles, or roughly the distance from Earth to the Sun minus a bit. At that distance, to create a detectable 3 nanosecond time dilation across the entire planet, the object would need a mass of approximately 2.1 x 10 circumflex 14 kilograms. You wait for that to mean something. That's 210 trillion kilograms, Sarah translates. For comparison, the Great Pyramid of Giza masses about 6 million metric tons. 3I/Atlas has the mass of about 35,000 Great Pyramids. Packed into a sphere roughly 340 meters across, about the height of the Eiffel Tower. The numbers are starting to make your head spin. And that gives us the density you mentioned, the 22.4 grams per cubic centimetre. Correct. Which brings us to the really weird part. Sarah pulls up a periodic table. See osmium here, element 76. Atomic number 76, meaning 76 protons in each nucleus. It's the densest stable element that occurs naturally. Density 22.59 grams per cubic centimetre. 3I/Atlas clocks in at 22.4. It's in the right ballpark. But here's the problem: osmium is incredibly rare. In Earth's entire crust, osmium makes up about 0.05 parts per billion. You're more likely to find gold. So an osmium asteroid would be essentially impossible, Sarah finishes. Osmium forms in supernova explosions and neutron star mergers. It's scattered throughout the universe in trace amounts. The odds of getting enough osmium to coalesce into a 340-metre sphere astronomically low. Literally, you can see where this is going. So, if it's not osmium, what could it be? Sarah hesitates. This is the moment where scientific certainty meets uncomfortable speculation. There are a few possibilities. 1, it could be an iron-nickel core from a destroyed protoplanet, compressed by extreme forces we don't fully understand. 2, it could be some form of matter we haven't encountered before, maybe an exotic alloy that forms under conditions that don't exist in our solar system. 3, she trails off. 3, you prompt. 3, it could be manufactured, Sarah says quietly. Look, I'm not saying aliens. I'm saying that the density profile is consistent with certain compressed materials that we create in laboratories. Tungsten carbide, for example, used in industrial applications. Density around 15.6 grams per cubic centimetre. Some tungsten-rhenium alloys can hit 20. There are theoretical materials, osmium-iridium alloys, certain ceramic metal composites that could theoretically reach 22.4 if you had the manufacturing capability. The room suddenly feels smaller. You're saying this could be artificial. I'm saying the data doesn't rule it out, Sarah corrects. And that's significant because usually, with natural objects, we can rule out artificial origins immediately. With Oumuamua back in 2017, there was debate because of its weird tumbling motion and slight acceleration that couldn't be explained by outgassing. But most scientists settled on it being a natural object, probably a nitrogen iceberg from a Pluto-like world, with 3 I/Atlas. The density is the smoking gun. It's right at the edge of what's naturally possible. You think about this. What would it take to confirm whether it's artificial or natural spectroscopy? Sarah answers immediately. We need to analyse the light reflecting off its surface. Different materials absorb and reflect different wavelengths. Natural space rocks have signatures we recognise: silicates, iron, nickel, carbon compounds. Manufactured materials would show different patterns. The problem is, 3 I/Atlas is moving fast and it's already past its closest approach to Earth. We've got maybe 60 hours left before it's too far away for detailed spectroscopic analysis. She pulls up an image from the Hubble Space Telescope, a tiny bright dot against the blackness of space. This is the best optical image we have. It's not much, but look at the spectral data beneath it. The data shows peaks and valleys across different wavelengths of light. Sarah points to a particular section. See this absorption line here that's consistent with iron oxide? And this one consistent with carbonaceous material? So far, nothing unusual. But this peak here, she indicates a sharp spike in the ultraviolet range. This doesn't match anything in our databases. Not exactly. What does that mean? It means either we're looking at a mineral composition that hasn't been catalogued yet, or we're looking at something that's been processed, refined, like the difference between raw iron ore and steel. One occurs naturally, the other requires technology. Your phone buzzes. It's a message from your supervisor at NIST Emergency Video Conference in 30 minutes. All atomic clock facilities, mandatory attendance. Sarah sees your expression. You got the call too, you nod. What do you think this is about? My guess they've got new data, probably from LIGO or Virgo, the gravitational wave detectors. Those instruments are sensitive enough to pick up space-time ripples from colliding black holes billions of light-years away. If 3 I/Atlas created a measurable gravitational wake, LIGO definitely saw it, and if LIGO saw it, they can tell us things about the object's internal structure that optical telescopes can't. She starts packing up her laptop. There's something else you should know. About 30 hours before you detected the clock shift, 2 different research groups independently reported anomalous gravitational readings. One was monitoring Earth's gravitational field using satellite data. The other was running a quantum gravity experiment in Australia. Both detected what they described as a precursor wave, like a gravitational shadow being cast before the actual object arrived. Is that normal? No, Sarah says flatly. That's not normal at all. Gravitational effects propagate at the speed of light. You don't get advance warning unless... She pauses, choosing her words carefully. Unless the object is massive enough and moving fast enough that its gravitational influence arrives before our optical telescopes can see it, which would require either tremendous mass more than we think 3 I/Atlas has, or some kind of gravitational focusing effect we don't understand. You're about to ask another question when Sarah's phone rings. She glances at the screen and her expression changes. It's Geneva, the International Astronomical Union Emergency Committee. She answers dreary. Doctor, Chen speaking. You can't hear the other side of the conversation, but you watch Sarah's face cycle through surprise, confusion, and something that might be fear. When? She asks. How certain are they? A pause. I understand. Yes, I'll be on the call. She hangs up. What happened? Sarah looks at you for a long moment. That was Dr. Nakamura from the IAU. They've been running trajectory simulations, working backward to figure out where 3 I/Atlas came from. Standard procedure: you track an object's path, account for gravitational influences from planets and the sun, and extrapolate backward through space. And 3I/Atlas didn't come from random interstellar space. Its trajectory traces back to a specific star system. A G-type main sequence star similar to our Sun, located 47.3 light-years away in the constellation Pictor, system designation HD 40307. And here's the kicker: HD 40307 has 6 confirmed exoplanets. One of them, HD 40307G, is a super-Earth in the habitable zone. Last year, the James Webb Space Telescope detected oxygen and methane in its atmosphere, potential biosignatures. The implications hit you like cold water. You're saying this object came from a solar system that might have life. I'm saying, Sarah corrects carefully, that the trajectory is consistent with an origin point in that system, which means either this is the most incredible coincidence in astronomical history, or... She doesn't finish the sentence. She doesn't have to, because if 3I/Atlas originated from a system with potential biosignatures, and if its density suggests possible artificial manufacturing, and if it created a gravitational signature precise enough to shift every atomic clock on Earth by exactly 3 nanoseconds, then maybe, just maybe, that 3 nanosecond shift wasn't an accident. Maybe it was a calling card, a way of saying we're here, we're real, and we know you're watching. And if that's true, then the next 58 hours aren't just about studying an interstellar object. They're about preparing for a truth that changes everything. We are not alone. And someone or something just announced their arrival using the most precise measurement tool humanity has ever created. The question is, what comes next? You're on a video call with 47 scientists scattered across the globe. It's 2:17 p.m. Eastern Time now, 22 hours since the clock shift, and you're looking at a grid of faces that collectively represent humanity's best understanding of physics, astronomy, and orbital mechanics. Most of them haven't slept. You can tell by the coffee cups, the dishevelled hair, the way people keep rubbing their eyes between speaking. Doctor Maria Rodriguez from the Jet Propulsion Laboratory is presenting, and her screen shows something that looks like a 3-dimensional spaghetti mess trajectory, lines in different colours, all converging on one point: Earth's position on November 12th. Let's start with what we know for certain. Maria begins, her voice carrying the particular exhaustion of someone who's been working non-stop. 3I/Atlas entered our solar system's detection range on November 1st at 0418 UTC. Initial detection came from Pan-STARRS 1 in Hawaii. They flagged it as unusual due to its velocity and trajectory angle. Within 6 hours, we had confirmation from 3 additional facilities: the Catalina Sky Survey in Arizona, the European Space Agency's optical ground station in Tenerife, and the Subaru telescope in Japan. She clicks to the next slide. Here's where things get interesting. Most objects we track: asteroids, comets, even previous interstellar visitors, we detect them, watch them for a few days, and gradually build up a trajectory model. With 3I/Atlas, we had something different, no? We had 11 days of continuous observation before closest approach, 11 days to watch, measure, and realise that what we were looking at didn't make sense. The screen shows a diagram of the solar system from above the flat disk of planetary orbits, looking like a bullseye target. Then a red line slashes through it at a nearly vertical angle, like someone taking a knife to a dinner plate. Orbital inclination 87.2 degrees to the ecliptic, Maria continues. For context, most objects in our solar system have inclinations under 30 degrees. Even Oumuamua, our first confirmed interstellar visitor in 2017, came in at 122 degrees steep. Yes, but it was retrograde, moving backward against the plane. 3I/Atlas is different. It's nearly perpendicular. It dove through our solar system almost straight down, like it was dropped from above. Someone unmutes. It's Doctor James Park from Seoul National University. Maria, can you show the velocity profile again? I want people to see the anomaly. Maria switches slides. This one shows a graph with velocity on the vertical axis and time on the horizontal. The line is almost perfectly straight except for two small bumps. Velocity at detection 87.3 km per second relative to the Sun. Maria says, "That's fast. Really fast. For comparison, Voyager 1, our fastest spacecraft, moves at 17 km per s. The average asteroid may be 25 km per s. At 87 km per s, this object was moving faster than 99.8% of everything we've ever tracked in the solar system. But here's what kept me awake last night." She zooms in on those two bumps in the graph. On November 4th, 3 days after initial detection, we measured a slight acceleration, 0.03 km per second gained over a 4-hour period. Then nothing constant velocity for 6 days. Then on November 10th, 2 days before closest approach to Earth, another acceleration, 0.04 km per s over 3 hours, then constant velocity again until it passed us. The video grid fills with scientists leaning closer to their cameras. "Comets accelerate," someone points out. "You recognize the voice, Doctor? Yuki Tanaka from JAXA, the Japanese Space Agency. Outgassing from solar heating creates thrust. We saw this with Oumuamua." "Right," Maria agrees. Except 3i/Atlas showed no outgassing signature. No coma, no tail, no detectable gas or dust ejection. The accelerations happened, but without any visible mechanism. And the timing is what bothers me. The first acceleration occurred when the object was 2.1 AU from the Sun, about twice Earth's distance. Way too far out for significant solar heating. The second acceleration happened at 0.9 AU, which is closer, but still no outgassing detected. Your supervisor, Dr. Patricia Hayes, unmutes. Could it be an observational error? Maybe we missed the outgassing due to the object's orientation? Maria shakes her head. We considered that, but we had spectroscopic monitoring from 4 different facilities using 3 different detection methods. If there was outgassing even a tiny amount, we would have seen it. The Hubble Space Telescope had a dedicated observation window specifically looking for this. Nothing. The object accelerated twice without any apparent propulsion mechanism. The silence on the call is heavy. Everyone knows what this implies, but nobody wants to say it. Dr. Hassan al-Rashid from the Mohammed bin Rashid Space Center in Dubai breaks the silence. Have we calculated the delta V required for those accelerations? And more importantly, what kind of energy expenditure would that represent? Maria was clearly waiting for this question. I'm glad you asked. The object's estimated mass, based on gravitational measurements, is 2.1 x 10 circumflex 14 kilograms. To accelerate that mass by 0.03 kilometers per s requires approximately 9.5 x 10 circumflex 19 joules of energy. That's roughly the energy output of 22,700 megatons of TNT. The largest nuclear weapon ever detonated, the Soviet Tsar bomber in 1961, was 50 megatons. We're talking about energy release equivalent to 454 Tsar bombers. And we detected no thermal signature, no radiation spike, nothing. You find yourself doing mental calculations, trying to make that number feel real. It doesn't work. The scale is too large. There's more, Maria continues, and somehow her voice gets even more serious. We've been analysing the trajectory not just forward from detection, but backward through space. Where did this object come from, Doctor? Park and his team at Seoul have been running simulations accounting for galactic rotation, stellar drift, gravitational perturbations from nearby stars, basically trying to trace this thing's path through interstellar space. James Park takes over the presentation. Thank you, Maria. What I'm about to show you represents 300 hours of computational time on one of the most powerful supercomputers in Asia. We traced 3/Atlas backward through space for 47.3 years. That's how long it would take an object moving at 87 kilometers per s to travel 1 light year. Roughly. We accounted for 847 different gravitational influences, including the movement of our own sun through the galaxy. The screen shows a star field with a dotted line tracing backward from our solar system. The line weaves through space, curving slightly as it passes near other stars, until it terminates at a single bright point. The trajectory traces back to HD 40,307 inches. Park says, a G-type star similar to our Sun, located 47.3 light-years away in the constellation Pictor. System characteristics 6 confirmed planets. One of them a super-Earth designated HD 40,307G in the habitable zone. Estimated travel time, assuming constant velocity 47.3 years, meaning 3I/Atlas would have departed that system around 1978 by our calendar. Someone whistles softly. You're not sure who? Now, before everyone jumps to conclusions, Park continues quickly. I need to emphasize that trajectory calculations over interstellar distances have enormous error bars. We're accounting for stellar movements, galactic rotation, gravitational perturbations we might have missed. Our confidence interval puts the origin somewhere within a sphere about 5 light-years in radius centered on HD 40307. There are 14 other star systems within that sphere, so while HD 40307 is the most likely origin point, it's not the only possibility. Dr. Sarah Chen, who's been quiet until now, unmutes. James, what's the probability that the trajectory alignment with HD 40307 is coincidental? Can you quantify that? Park nods. We ran Monte Carlo simulations basically throwing 10,000 random trajectories through interstellar space and seeing how many happen to pass through our solar system at the right angle and velocity. The answer? Approximately 1 in 340,000 trajectories from random directions would match what we observed. But if we weight the simulation toward objects originating from known star systems with confirmed exoplanets, the probability increases to about 1 in 1/200. Still long odds, but not impossible. You notice several scientists furiously taking notes. Someone's recording the call, probably multiple people. Maria Rodriguez takes over again. Let's talk about the 11-day observation window, because that's actually the strangest part of this entire event. Most interstellar objects move so fast that by the time we detect them, they're already leaving. Oumuamua. We had maybe 3 weeks of observation, and most of that was watching it disappear. 2I/Borisov. The second interstellar comet in 2019, we got lucky it was bright enough to track for months. But 3I/Atlas. It's like someone calculated the perfect trajectory to give us exactly enough observation time. She pulls up another diagram. Look at this. If 3I/Atlas had come in at 80 degrees inclination instead of 87, we would have detected it 30 hours earlier, but it would have passed Earth farther away, reducing observation quality. If it had come in at 93 degrees, we would have had better close approach data but less advance warning. The 87.2 degree angle is, and I'm choosing my words carefully here, suspiciously optimal for ground-based observation from Earth. Doctor, Patricia Hayes speaks up again. Maria, are you suggesting this trajectory was chosen deliberately? I'm suggesting, Maria replies carefully, that if I were planning to send a probe through an alien solar system, and I wanted to maximize observation time while minimizing risk of collision, I would choose a trajectory very similar to what we observed. High inclination to avoid planetary orbits, high velocity to minimize exposure to radiation and debris, time to pass close enough to the primary planet for detailed observation, but not so close as to risk gravitational capture or atmospheric entry. The video grid erupts. Multiple people trying to unmute and speak at once. Doctor. Hayes raises her hand, and gradually the chaos settles. One at a time, Hayes says firmly. Dr. Al-Rashid, you first. Hassan al-Rashid's face fills the main screen. Maria, if we entertain the hypothesis that this trajectory was planned, that raises an obvious question. How would whoever planned it know where Earth would be? Our planet's position changes constantly. To hit an 11-day observation window from 47 light-years away requires knowing Earth's orbital position 47 years in advance, with extraordinary precision. Exactly, Maria agrees. Which means either this is an incredible coincidence, or whoever sent this has been observing our solar system for longer than 47 years. Long enough to build an accurate orbital model of all the planets, long enough to calculate the optimal trajectory, and that suggests persistent observation, probably astronomical observation from their home system. You lean closer to your screen, but we've been broadcasting our presence for decades. Right radio, television, radar, all that leaks into space at light speed. If someone 47 light-years away has been listening, they've had plenty of time to learn about us. Maria nods. Our first television broadcast started in the 1930s. By 1978, when 3I/Atlas would have launched, those signals would have travelled about 40 light-years. Not quite to HD 40307, but close. However, here's the thing, those signals degrade with distance. By the time you're 20 light-years out, Earth's radio signature is incredibly faint. You'd need a receiver far more sensitive than anything we've built to detect it. So if someone at HD 40307 picked up our broadcasts, their technology is significantly more advanced than ours. Dr. Yuki Tanaka speaks up. What about the James Webb Telescope observations of HD 40307G, the biosignature detection? Can we correlate that with what we're seeing? Park switches slides. Good question. JWS observed HD 40307G in March 2024 as part of a habitability survey. They detected spectral lines consistent with molecular oxygen and methane in the atmosphere, both potential biosignatures. The combination's interesting because oxygen and methane react with each other. To maintain both in an atmosphere, you need a constant replenishment source. On Earth, that source is life. Photosynthesis produces oxygen. Biological decay produces methane. But we can't confirm life from spectroscopy alone. There are non-biological processes that could explain the signatures. But taken together, Sarah Chen adds. An exoplanet with biosignatures and an object from that system arriving here with suspicious trajectory characteristics and unexplained accelerations, the coincidences are piling up. Hayes cuts in. Let's focus on what we can measure. Maria, you mentioned the object is currently exiting our observation range. What's the timeline? As of now, 3I/Atlas is 1.2 astronomical units from Earth and receding at 87 kilometers per s. We have approximately 56 hours of useful observation time left before it becomes too distant for detailed spectroscopy. After that, we'll still be able to track its position for maybe another month, but we won't be able to analyze its composition or detect any further accelerations. It'll become just another dot of light, getting fainter every day until it disappears completely. 56 hours, Hayes repeats. So we need to prioritize. What are the critical observations we need to make before we lose the opportunity? Maria's already got a list ready. Priority 1, high-resolution spectroscopy from multiple facilities to confirm composition. Priority 2, radar imaging to get shape and rotation data. Priority 3, continued gravitational monitoring from atomic clock networks and LIGO Virgo to see if there are any other space-time anomalies. Priority 4, thermal imaging to check for any temperature variations that might indicate internal heat sources or propulsion systems. And Priority 5, Doctor. Al-Rashid adds, "We need to consider whether we should attempt communication. If there's any possibility this is an artificial probe, we should at least try transmitting a signal. The object is moving away from us at 87 kilometers per s, but radio waves travel at light speed. We could still reach it." The call goes quiet again. This is the big question, the one nobody wanted to ask. Hayes looks directly into a camera. "That decision is above our pay grade. That requires consultation with government officials, possibly the UN Office for Outer Space Affairs. We're scientists, not diplomats. Our job right now is to gather data and present it to the people who make those decisions." But even as she says it, you can see the doubt in her eyes. Because everyone on this call knows the truth if 3I/Atlas is artificial, if it was sent deliberately, if it came from a system 47 light-years away, then someone has been watching us for at least 47 years. Someone with technology advanced enough to build an interstellar probe that can navigate across light-years with precision, that can accelerate without visible propulsion, that can create gravitational signatures precise enough to shift atomic clocks by exactly 3 nanoseconds. And if they sent this probe 47 years ago, that means they saw something in 1978 or earlier that made them decide we were worth investigating. What did they see? What did we do that caught their attention across 47 light-years of empty space? Maria closes with one final thought. Whatever 3I/Atlas is natural or artificial, it's given us the most detailed data we've ever had on an interstellar object. We have trajectory data, velocity profiles, gravitational measurements, spectroscopic analysis, and 11 days of continuous observation. That's more information than we got from Oumuamua and 2I/Borisov combined. In 56 hours, that window closes. So whatever we're going to learn, whatever we're going to discover, it needs to happen now. The meeting ends. The video grid collapses. You're left staring at your own reflection in the black screen, and you realise your hands are shaking slightly, because somewhere out there, 2 astronomical units away and receding is an object that might be humanity's first confirmed contact with an alien intelligence. And you have 56 hours to prove it or to prove you're wrong. Either way, the answer will change everything. You're in a basement laboratory at MIT, surrounded by mass spectrometers and electron microscopes that cost more than most houses. It's 11:43 p.m. Eastern Time, now 44 hours since the clock shift, and Dr. Rebecca Torres is holding what looks like a small black rock in a pair of titanium tweezers, except it's not from 3I/Atlas. It's from a meteorite that fell in Chelyabinsk, Russia in 2013, and she's using it to make a point. "This is an ordinary chondrite," Rebecca says, rotating the sample under a microscope. "Came from the asteroid belt, probably got knocked loose millions of years ago, eventually hit Earth's atmosphere at about 19 kilometers per second. When it entered the atmosphere, the air friction was so intense that the outer layer melted, creating what we call a fusion crust. See this dark coating? That's the rock's surface literally re-solidifying after being vaporized. You look through the eyepiece. The fusion crust looks like burned caramel, smooth, glossy, with tiny bubble-like imperfections. Now look at this," Rebecca says, switching samples. "This one's from the Allende meteorite, a famous carbonaceous chondrite that fell in Mexico in 1969. Different composition, higher carbon content, hydrated minerals, organic compounds. This thing is 4.567 billion years old, older than Earth itself. It's leftovers from the solar system's formation, unchanged since the sun was born. When we analyse meteorites like this, we're literally holding primordial material, the building blocks of planets." She places both samples side by side under a comparison microscope. Ordinary chondrites are mostly iron, nickel, magnesium, and silicon. density around 3.5 grams per cubic centimetre. Carbonaceous chondrites are lighter, maybe 2.2 grams per cubic centimetre, because of all that carbon and water ice. Iron meteorites, chunks of metal from disrupted asteroid cores, can hit 7.8 grams per cubic centimetre. These are the three main types we find on Earth, representing billions of years of cosmic collisions. And none of them come close to 22.4 grams per cubic centimetre. You finish. Not even close. Rebecca confirms. She pulls up a density chart on her computer. Look at this. I've compiled density measurements from 8,347 meteorite samples and collections worldwide. The densest natural meteorite ever found, the Hoba meteorite in Namibia, an iron-nickel mass weighing 60 tons, density 7.9 grams per cubic centimetre. The densest mineral found in meteorites, iridium, inclusions in some iron samples 22.56 grams per cubic centimetre. And we're talking about microscopic grains, not bulk composition. She zooms in on a particular data point. 3I/Atlas, with its 22.4 G per cubic centimetre bulk density, would need to be almost entirely composed of osmium-iridium alloy, not just containing it, but made of it. Do you understand how impossible that is from a formation standpoint? You're starting to, but you want to hear her explain it. Okay, quick geology lesson. Rebecca continues, warming to her subject. When a solar system forms, you start with a collapsing cloud of gas and dust. Heavy elements like iron, nickel, iridium, osmium, they sink to the centre during planetary formation because of gravity. That's why Earth has an iron core. The lightest materials, hydrogen, helium, water, silicates stay in the outer layers. This is called differentiation, and it's why planets have layers. She draws a quick diagram on her tablet. Now, to get a 340-metre object that's pure osmium-iridium, you'd need to somehow extract just the core material from a planet or large asteroid, separate it from all the lighter surrounding material, and then, and this is the impossible part, get it to stay together as a discrete object. Because here's the thing, osmium-iridium alloys form in the most violent events in the universe. Supernovae, neutron star mergers, events so energetic they literally create heavy elements through nuclear fusion. So, where would 3I/Atlas get its density, you ask? Rebecca leans back in her chair. That's the trillion-dollar question. Natural formation, I can think of exactly one scenario. Imagine a super-Earth planet, maybe 5, 10 times Earth's mass. In the habitable zone of a star, it forms normally, with a dense metallic core, then something catastrophic happens, maybe a collision with another planet, or a close encounter with a massive star. The outer layers get stripped away, but the core remains intact. Over time, tidal forces or additional collisions break off chunks of that core. One of those chunks, maybe the size of a small mountain, gets ejected from the system at high velocity, eventually travelling through interstellar space for millions of years until it happens to pass through our solar system. She pauses. The odds of that scenario I'd estimate maybe 1 in 10 billion. But it's technically possible, so we can't rule it out. What about manufactured materials, you venture? Rebecca's expression shifts. Now we're in my uncomfortable zone. Look, I'm a geologist. I study rocks, natural materials. But I can't ignore the data, so let's talk about it. On Earth, we can manufacture materials with densities exceeding natural limits. Tungsten carbide for industrial drill bits, 15.6 G per cubic centimetre. Depleted uranium for armour-piercing ammunition, 19.1 G per cubic centimetre. We've even created osmium-iridium alloys in laboratories that hit 22.5 G per cubic centimetre, though only in tiny samples. She pulls up a file marked Classified Materials Science. You notice she doesn't ask if you have clearance. This is from Los Alamos, Rebecca says quietly. They've been studying ultra-dense materials for decades. Nuclear weapons cores use compressed plutonium that can reach densities of 19.8 G per cubic centimetre under extreme pressure. There's theoretical work on neutronium, the material neutron stars are made of, which has densities around 10 circumflex 14 GCM3, but that's obviously not stable outside a neutron star's gravitational field between normal matter and neutronium. There's a gap, and right in that gap, at the upper end of what's physically possible for stable matter, is 22.4 G per cubic centimetre. The exact density of 3I/Atlas, you note, within our margin of error, yes. Rebecca closes the file. If, and I want to stress that if 3I/Atlas is manufactured, then whoever made it has materials science capabilities at or slightly beyond our current technology. Not wildly advanced, not physics breaking, just better, more refined, which actually makes the artificial hypothesis more unsettling, because it suggests we might be dealing with a civilization only a few hundred years more advanced than us, not thousands or millions. Your phone vibrates. It's a message from Dr. Chen. Spectroscopy results from Keck Observatory. You need to see this. Rebecca notices your expression. What is it? New spectroscopy data? Want to see it together? She's already reaching for her laptop. The file from Keck Observatory is enormous. 47 gigabytes of spectroscopic data taken over an 8-hour observation window. Dr. Chen's included a summary analysis, and you read it aloud. Spectral analysis of 3I/Atlas reveals absorption lines consistent with iron oxide, Fe2O3, carbonaceous compounds, CH bonds, and silicate minerals, all typical of asteroidal bodies. However, 3 anomalous absorption features detected in the ultraviolet range 247 nanometers, 284 nanometers, and 312 nanometers do not correspond to any known natural mineral signatures. Analysis suggests possible presence of synthetic compounds or exotic alloys not found in meteorite databases. Rebecca grabs the laptop and starts pulling up comparison spectra. Okay, let's break this down. Iron oxide that's rust. Basically, you get that on any object that's been exposed to oxygen, even trace amounts in space. Carbonaceous compounds, organic molecules, very common in asteroids. Silicates, rocky material, the stuff that makes up most of Earth's crust. All normal. She highlights the 3 anomalous wavelengths. But these are weird. An absorption line at 247 nanometers suggests something is absorbing specifically UVC radiation. What absorbs UVC certain atmospheric gases? Some organic molecules. And she pauses to check a reference, certain ceramic metal composites we use in spacecraft heat shields. Ceramic metal composites, you repeat. That sounds manufactured. It does, doesn't it? Rebecca pulls up another spectrum, this one from a sample of spacecraft heat shield material. Look at this. Reinforced carbon-carbon composite. Used on the space shuttle's nose cone. Peak absorption at 249 nanometers. That's within 2 nanometers of the 3I/Atlas anomaly. Could be coincidence. Could be convergent materials science. Maybe there's only one optimal way to make ultra-heat-resistant materials, and any advanced civilization would discover the same compounds we have. She moves to the second anomaly. 284 nanometers. This one's interesting because nothing in our meteorite database shows absorption here. But you know what does certain transition metal nitrides? Titanium nitride. Zirconium nitride, we use these for tool coatings because they're incredibly hard. They're also excellent at absorbing specific wavelengths of UV light. And the third one, 312 nanometers. Rebecca frowns at the screen. This is the one that keeps me awake. 312 nanometers is right in the range where certain photochromic materials that change properties when exposed to light, show absorption peaks. We use photochromic compounds in everything from sunglasses that darken in sunlight to optical data storage. But I've never seen a natural mineral with an absorption line at exactly 312 nanometers. She runs a few calculations. Here's what bothers me. These three absorption lines, 247, 284, 312, they're remarkably evenly spaced. In wavelength terms, that's 37 nanometer intervals. Natural absorption lines are determined by electron energy levels in atoms, and they don't typically space themselves in nice round numbers. But if you were engineering a material for specific optical properties, say, to reflect certain wavelengths and absorb others, you might choose evenly spaced absorption bands for manufacturing simplicity. You stare at the data, so these could be engineered materials. Could be, Rebecca emphasizes. Or it could be a natural material with unusual crystalline structure that we haven't encountered before. The universe is vast, and we've only sampled a tiny fraction of possible mineral compositions. Just because we haven't seen it doesn't mean it can't exist naturally. She pulls up another file. This one shows comparison data from Oumuamua and 2I/Borisov, the two previous confirmed interstellar objects. Oumuamua showed spectral characteristics similar to Pluto's surface nitrogen ice. Tholins, organic compounds. 2I/Borisov was clearly a comet, lots of water ice. Carbon monoxide, dust. Both were consistent with natural objects formed in other solar systems. 3I/Atlas. The baseline spectrum looks natural, but these three anomalies are like finding a Wi-Fi signal in a forest. It doesn't belong. Your phone vibrates again. This time it's a conference call notification. Urgent density anomaly analysis, all relevant personnel. Rebecca sees it too. That's the same call. We should take this. The video conference connects. You recognize many of the faces from previous calls: Dr. Hayes, Dr. Park, Dr. Chen. But there are new faces too, including someone with a military uniform and a name tag reading Colonel David Morrison, USAF Space Command. Colonel Morrison speaks first, which tells you everything about how seriously this is being taken. Thank you all for joining on short notice. I'm going to cut to the chase. As of 1800 hours today, the Department of Defense has elevated 3I/Atlas to Category 1 observation priority. That's the same designation we give to potentially hazardous near-Earth asteroids and foreign satellites in strategic orbits. What I'm about to share is classified secret, and I need verbal confirmation from each participant that you understand the security implications. One by one, people confirm. When it's your turn, you say confirmed and wonder how your life got here. Good, Morrison continues. 72 hours ago, a Defense Support Program satellite detected a thermal anomaly coinciding with 3I/Atalus's second acceleration event. The anomaly lasted 47 seconds and registered approximately 3400 Kelvin, hot enough to glow orange if you could see it with naked eyes. That's roughly the temperature of molten iron. He pulls up a thermal image, a bright white dot against a black background, with temperature scales on the side. This satellite is designed to detect missile launches by spotting the heat signature of rocket exhaust. It picked up 3I/Atlas by accident because the object happened to pass through its field of view during a routine scan. The thermal signature is inconsistent with solar heating, impact events, or any known natural phenomenon. Doctor, Torres unmutes. Colonel, what's the energy output we're looking at? Approximately 8.7x10 circumflex 12 watts sustained over 47 seconds. That's 8.7 terawatts, roughly the entire power consumption of the United States for about 20 minutes, released in less than a minute. The silence on the call is absolute. Now here's the key point, Morrison continues. The thermal emission coincided exactly with the measured acceleration. When the object sped up by 0.04 kilometers per s, it got hot. That suggests a direct connection between the heat and the velocity change. And that, ladies and gentlemen, looks an awful lot like propulsion. Doctor, Park speaks up. What kind of propulsion did you detect any exhaust plume? Any ejected material? Negative. No plume, no exhaust trail, no ejected mass that we could detect. Whatever heated up, it was the object itself, or something on its surface. Our analysts have been comparing this to known propulsion systems, chemical rockets, wrong thermal profile too sustained, not enough peak temperature, ion drives wrong energy signature, nuclear thermal closer, but still doesn't match. What we're looking at doesn't correspond to any propulsion technology currently in use by any nation on Earth. Rebecca's hand goes to her mouth. You notice several other scientists with similar reactions. There's one more thing, Morrison says, and somehow his tone gets even more serious. We've been running simulations on the object's trajectory, trying to predict its path after leaving our solar system. Based on current velocity and heading, 3I/Atlas will pass within 0.3 light-years of Proxima Centauri in approximately 11,400 years. Proxima Centauri, as many of you know, has at least 2 confirmed exoplanets, including one in the habitable zone. We don't know if that's coincidental or intentional, but it's worth noting. Doctor, Hayes clears her throat. Colonel Morrison, are you suggesting this object might be an interstellar probe conducting a multi-system survey? Morrison's face is carefully neutral. I'm suggesting we can't rule it out. And if it is a probe, then its creators have technology that allows for 1. Precise interstellar navigation across 47 light-years. 2. Propulsion without visible exhaust or reaction mass. 3. Materials science capable of producing ultra-dense structures. And 4. Engineering that functions reliably after 47 years of space travel. That's a technological profile we need to take seriously. He pauses. In 38 hours, 3I/Atlas will be too far away for our best telescopes to conduct detailed analysis. After that, it becomes a point of light, then nothing. We have 1 narrow window to gather every piece of data possible. Secretary of Defense has authorized the deployment of additional orbital assets for observation. NASA and ESA are coordinating their deep space network for continuous radio monitoring, and we're consulting with SETI, the Search for Extraterrestrial Intelligence, about whether we should attempt to transmit a signal. A signal, someone asks. You mean try to communicate with it? That decision hasn't been made, Morrison says carefully. But it's under consideration at the highest levels. If there's any chance this is an artificial probe, the opportunity to attempt communication may not come again in our lifetimes. However, there are obvious concerns about revealing our technological capabilities. Our location, though, if this object came from HD 40307, they already know where we are. The call continues for another 40 minutes, with scientists proposing observation strategies, analysis protocols, data sharing agreements. But you're only half listening, because you're thinking about something Rebecca said earlier. A civilization only a few hundred years more advanced than us. Not millions of years. Not godlike beings with incomprehensible technology. Just neighbours. Neighbours who figured out interstellar travel, materials science, and autonomous navigation a few centuries before we did. Neighbours who, 47 years ago, aimed a probe at our solar system with enough precision to give us an 11-day observation window and create a 3-nanosecond gravitational signature that every atomic clock on Earth could detect. Why 3 nanoseconds? Why that exact amount was it calculated a signature? A calling card that said, we know you have atomic clocks. We know you can measure gravitational effects. Here's proof we exist. The call ends. Rebecca looks at you. Are you thinking what I'm thinking? That this might be first contact? That this might be first contact? She confirms. And we have 38 hours to figure out if we're right. You're standing in the control room of the Laser Interferometer Gravitational Wave Observatory LIGO in Livingston, Louisiana. It's 7:23 a.m. Central Time, now 52 hours since the clock shift, and you're looking at data that shouldn't exist. Doctor. Michael Jang, LIGO's lead physicist, has his arms crossed and is staring at the same screen with an expression somewhere between fascination and disbelief. Okay, let me make sure I understand this correctly. You say slowly, LIGO detected 3 I/Atlas before the atomic clocks did. Not just before, Michael corrects. 37 minutes before. Look at the timestamp. He points to the data stream. November 12th, 3:10 a.m. UTC. That's when we first detected gravitational wave activity consistent with a massive object passing through the inner solar system. The atomic clock network didn't register the deviation until 3:47 a.m. That's a 37-minute gap. You try to process this, but gravitational effects travel at the speed of light. Right. How can LIGO detect something 37 minutes before it happens? Michael grins, but it's not a happy grin. It's the grin of someone who's spent all night running calculations and keeps getting the same impossible answer. That's exactly the question that's been keeping me awake. Gravitational waves ripples in space-time caused by accelerating masses do indeed propagate at light speed. Einstein proved it, and we've confirmed it with observations of colliding black holes. So theoretically, LIGO and the atomic clock should detect the same event simultaneously, maybe with a few seconds difference depending on the object's position. Not 37 minutes. He pulls up a visualization. Here's what LIGO saw. This is gravitational wave data from both our Livingston facility and our twin facility in Hanford. Washington. The signals match perfectly, which rules out local interference. Both detectors saw the same thing at the same time. The screen shows a wave pattern, subtle undulations against a baseline. It looks almost like a heartbeat monitor, except the peaks and valleys are incredibly precise. Now watch what happens when I overlay the atomic clock data. Michael adds another layer. The second wave pattern starts 37 minutes after the first, but the shapes are remarkably similar. See that same general signature, same duration 11.3 seconds, but offset by 37 minutes. It's like we saw the shadow before we saw the object casting it. That's impossible, you say, because it is. I agree. So let's talk about why it happened anyway. Michael sits down and pulls up a complex diagram of Earth, with curved lines representing gravitational fields. LIGO works by measuring infinitesimal changes in space-time. We shoot lasers down 2 perpendicular 4-kilometre-long tunnels and measure how long the light takes to return. When a gravitational wave passes through, it literally stretches space-time in one direction and compresses it in the perpendicular direction. We can detect changes as small as 1/1000th the diameter of a proton. He zooms in on the data. What we detected at 3:10 a.m. wasn't the same as what the atomic clocks detected at 3:47. The atomic clocks measured time dilation, a static effect caused by the object's mass-curving space-time. But LIGO detected something dynamic. A propagating disturbance. A wave. Like the object was creating ripples as it moved. Exactly like that. Except here's the weird part, the amplitude is all wrong. When we detect gravitational waves from colliding black holes, each one may be 30 times the mass of our sun, the signal is incredibly faint. We're talking about space-time distortions of 10 circumflex 21 meters. But 3 I/Atlas, its mass is maybe 1/10 of a single asteroid-like Ceres. It should be completely undetectable by LIGO. Yet we measured a signal strength of 3.7 x 10 circumflex 20 meters, about 10 times stronger than it should be for an object of that mass. You lean closer to the screen. So, either your measurements are wrong, which they're not, because Hanford confirmed everything independently, or the object's gravitational field is stronger than its mass suggests. Michael points at you. Now you're getting it. There are only a few ways that's possible. One, the object is more massive than we think, which contradicts the atomic clock measurements. Two, the object is made of exotic matter with unusual gravitational properties, which sounds like science fiction. Three, the object has an active gravitational manipulation system, which sounds even more like science fiction. Or four. He trails off. Four, you prompt. Four, the object itself isn't creating the gravitational waves. Something attached to it is. Something that generates a gravitational field independent of the object's actual mass. The room feels colder suddenly. You're talking about artificial gravity generation. I'm talking about something that looks a lot like it. Yes. Michael pulls up another file. After we detected the initial wave at 3:10, I went back through our data archive. LIGO's been operating continuously since 2015 with upgrades in 2020. We've detected 90 confirmed gravitational wave events, mostly binary black hole mergers, a few neutron star collisions. But we also flag thousands of potential signals that don't meet our confirmation threshold. Noise, cosmic rays, seismic activity, that sort of thing. He opens a filtered data set. So I asked our AI analysis system to search for any gravitational wave signatures similar to the 3I/8LAS event. Any time in the past 9 years where we detected a brief, localized gravitational disturbance that didn't match our black hole or neutron star templates. Guess what I found? More objects like 3I/Atlas. 17 of them, Michael's voice is quiet. 17 separate detections between 2015 and now, all brief under 30 seconds, all localized to our solar system, all dismissed as instrumental artifacts or noise because they didn't fit our models. But when I compare them to the 3I/Atlas signature, they're matches. Not perfect matches, but close enough that they're clearly the same phenomenon. He pulls up a timeline showing 17 small peaks scattered across 9 years. If these are all real detections, and after seeing 3I/8LAS, I think they are, then we've been visited by interstellar objects at least 17 times in the past decade. We just didn't recognize what we were seeing. Your mind races. Have you correlated these with optical observations? Did any of them coincide with detected asteroids or comets? That's the thing. I've been cross-referencing with NEO surveys, Pan-STARRS, Catalina Sky Survey, all the major detection networks. Of the 17 gravitational wave events, only 3 correspond to optically observed objects. The other 14 we saw the gravitational signature, but no one spotted the actual object, which means either they were too small or dark to detect optically, or they was actively avoiding detection. You finish? Michael nods slowly. I'm not comfortable making that claim in a peer-reviewed paper, but yeah, that's the implication. 17 objects in 9 years, most of them undetected optically, all creating gravitational signatures stronger than their mass should allow. And 3I/Atlas is the only one that happened to pass close enough and bright enough for us to study in detail. Your phone buzzes. It's Doctor. Chen again. LIGO results confirmed by Virgo in Italy and Kagra in Japan. All 3 facilities detected the 3:10 AM signal independently. This is real. You show Michael the message. He nods. Yeah, I've been on calls with Virgo and Kagra all night. They're seeing exactly what we're seeing. Virgo actually detected the signal 0.7 seconds before we did, which makes sense given the object's trajectory and the facility's relative positions. The timing triangulation confirms the source was 3I/Atlas, not some terrestrial interference. He pulls up a global map showing the 3 gravitational wave detectors. Here's what's interesting about the timing. The signal hit Virgo first, then LIGO Livingston 0.7 seconds later. then LIGO-Hanford 0.3 seconds after that, then Cagra 1. 2 seconds after Virgo. Those intervals are consistent with a gravitational wave propagating at light speed from a source approximately 0.84 AU away. The math works perfectly. Except for the 37-minute gap between the gravitational wave and the time dilation, you point out. Right, that's the part I can't explain. Michael opens a notebook filled with equations. I've been running models all night. Best hypothesis I've got, what if 3I/Atlas generated two different gravitational effects? The first one, the wave we detected at 310, was an active emission, like a pulse or a signal. The second one, the time dilation at 347, was the passive effect of its mass as it reached closest approach to Earth. Two different phenomena, 37 minutes apart, both gravitational in nature. An active emission. You consider this. Like it intentionally created a gravitational pulse. It's the only explanation that fits the data. And if that's true, it raises some pretty wild questions. Like why emit a gravitational pulse 37 minutes before closest approach? Was it a navigation ping, like sonar? Was it testing our detection capabilities, or he hesitates? Was it a signal, a deliberate attempt to get our attention using a method we definitely notice? You think about the 3 nanosecond clock shift. It worked! We noticed! Yeah, we did. Michael closes his notebook. There's something else. The gravitational wave we detected. It wasn't a simple pulse. It had structure, modulation. He pulls up a detailed wave analysis. The signal isn't just a smooth curve. It has tiny variations. Peaks within peaks. See these micro fluctuations? At first I thought they were noise, but they're too regular. The pattern repeats every 0.0137 seconds. That's about 73 cycles per second, 73 Hertz. And before you ask, yes, I've checked for environmental interference at that frequency. Earth's seismic noise, power grid harmonics, local traffic, nothing matches. Could it be the object's rotation rate? That's what I thought too, but spectroscopic data from Keck shows 3I/Atlas rotating at approximately 0.4 revolutions per hour. That's way too slow. The 73 Hz modulation is something else, something internal. You stare at the modulated wave pattern, 73 Hz. A frequency with no obvious natural explanation, embedded in a gravitational wave signal that arrived 37 minutes before the object's closest approach, detected by 3 independent facilities on 2 continents. Michael, you say carefully, what if the modulation is information? What if it's a carrier wave? His expression suggests he's already considered this. I've run the signal through every demodulation algorithm I can think of. FM, AM, phase shift keying, frequency hopping, all the standard radio transmission techniques. Nothing produces coherent data. Either it's not information, or it's encoded in a way we don't recognize. Or it's not meant for us to decode yet. You suggest. Maybe it's a test. Send a signal, see if anyone notices. See if anyone tries to decode it. Evaluate their technological level based on their response. Michael leans back in his chair. You know what's scary? That actually makes sense. If I were designing a first contact scenario, I might do exactly that. Send a probe through an alien solar system, emit a gravitational signal that only a civilization with advanced physics could detect, encode something in the signal, and see what happens. It's self-filtering. Only species advanced enough to have gravitational wave detectors would even know the signal existed. Your phone rings. It's Dr. Hayes from NIST. You put her on speaker. I'm assuming you're with Dr. Zhang? Hayes says without preamble. Have you seen the LIGO data? We're looking at it now. You confirm. Good, because we've got a bigger problem. LIGO detected the signal at 3:10 a.m. Atomic clocks detected the deviation at 3:47 a.m. But there's a third detection we just discovered. The squids picked up something at 2:51 a.m. Squids, Michael asks. Superconducting quantum interference devices. Hayes explains, they're ultra-sensitive magnetometers used for detecting tiny magnetic fields. We have a network of them for measuring Earth's magnetic field variations, solar wind effects, that sort of thing. At 2:51 a.m. on November 12th, every squid in the network detected a brief magnetic anomaly. Duration 11.3 seconds, amplitude approximately 0.7 nanotesla, barely above detection threshold, but definitely there. Michael's already pulling up a timeline. So we have magnetic anomaly at 251, gravitational wave at 310, and time dilation at 347. That's 3 separate detections, 90 minutes and 37 minutes apart. Correct, Hayes confirms. And here's the kicker. All 3 events lasted exactly 11.3 seconds, same duration, different phenomena, offset in time. That's not coincidence. You feel a chill run down your spine? It's a sequence. 3 separate signals, deliberately spaced. That's what we think too, Hayes says. We're calling it the Trinity signature, 3 distinct physical effects, all precisely timed, all traceable to 3I/Atlas. The question is, what does it mean? Michael starts sketching on his tablet. Electromagnetic signal at 251, gravitational wave at 310, time dilation at 347. If these were intentional, they're demonstrating mastery of 3 fundamental forces: electromagnetism, gravity, and if the time dilation was controlled rather than passive space-time manipulation, that's a hell of a calling card. Or a warning. You add, showing us what they're capable of, Hayes continues. We've been analysing the magnetic signature, like the gravitational wave. It shows modulation. But here's what's interesting, the modulation frequency is different. The magnetic pulse modulated at 137 Hz. The gravitational wave modulated at 73 Hz. 2 different frequencies, both whole numbers, both in the range that suggests intentional encoding. 137 and 73 inches, Michael repeats. Those numbers mean anything. You grab your phone and start searching. 137. That's close to the fine structure constant. It's approximately 1/137th one of the fundamental constants in physics. It describes the strength of electromagnetic interaction. Some physicists call it the most mysterious number in physics. And 73 inches, Michael asks. You keep searching. 73 is... Wait. 73 is the 21st prime number. Its mirror, 37 is the 12th prime number, and 12 reversed is 21. It's a mathematically interesting number, the Sheldon number, named after a character on The Big Bang Theory who called it the best number. Michael laughs, but it's strained. So, we have 137 related to electromagnetic interaction modulating the electromagnetic signal, and 73 a mathematically interesting prime modulating the gravitational signal. If someone were trying to demonstrate that these signals were artificial, that they understood physics and mathematics, this is exactly how they do it. Hayes speaks up. There's one more thing. We've calculated the energy required to generate each signal, the magnetic pulse approximately 10 circumflex 11 joules. The gravitational wave approximately 10 circumflex 14 joules. The time dilation effect approximately 10 circumflex 16 joules. Based on the mass energy necessary to curve space-time to that degree, that's an increase by a factor of 1000 each time. 3 signals, escalating energy levels, each one demonstrating control over a different fundamental force. You summarise. This isn't random, this is deliberate. Agreed, Hayes says. Which brings us to the critical question: do we respond? We have approximately 32 hours before 3I/Atlas exits our effective communication range. If we're going to transmit any kind of signal, radio, laser, whatever, we need to decide now. The UN Security Council is convening an emergency session in 3 hours. They're asking for a scientific recommendation: attempt communication or maintain observational silence. The weight of that question settles over the room. You're being asked to help decide whether humanity should announce its presence to whatever intelligence might be listening on the other end of that signal. Michael speaks first. If they came from HD 40307, they already know we're here. They aimed this thing at our solar system 47 years ago. Staying silent doesn't hide us. They've known about us for at least half a century. But there's a difference between passive observation and active communication. You counter. Right now, they know Earth exists and has developed technology. If we transmit, we reveal our current capabilities, our languages, our mathematics, our cultural context. That's a lot of information. Or we send something simple. Hayes suggests a mathematical sequence, prime numbers, the Fibonacci sequence, something that proves we detected their signal and understood it was artificial, without revealing too much about ourselves. You think about the 3 nanosecond signature, about the 73 Hz and 137 Hz modulations, about 17 previous objects that passed through our solar system undetected, except by gravitational wave observatories. They're not just exploring, you say slowly. They're testing us. Each object that passed through, they were probably all equipped with sensors, gathering data, assessing our technological development. And 3I/Atlas is different because we finally reached the threshold where we could detect it. We built atomic clocks precise enough to measure 3 nanoseconds. We built gravitational wave detectors sensitive enough to spot the signal. We've passed their test. Michael nods, which means they're expecting a response. The Trinity signature, it's not a warning, it's an invitation. They're saying, we know you can detect us now. Here's proof we're artificial. Here's proof we understand physics. Your move. Hayes is quiet for a moment. If you're right, and we don't respond, we're sending a message too. We're saying either we didn't understand the signal, which means we're not as advanced as they thought, or we understood it and chose not to respond, which could be interpreted as hostility or fear. Damned if we do, damned if we don't, Michael mutters. Not necessarily. You say, what if our response isn't a message? What if it's an action? They demonstrated 3 different phenomena: electromagnetic, gravitational, temporal. What if we demonstrate the same thing back? Show them we can manipulate those forces too, match their calling card with our own. Hayes sounds intrigued. How would we do that? The magnetic signal is easy. We have powerful electromagnets. We could generate a pulsed magnetic field that LIGO would detect. The gravitational wave is harder, but there might be a way to create a detectable disturbance using high-energy physics. And the time dilation? Okay, that one's beyond us right now. But 2 out of 3 might be enough to show we understood. Michael is already shaking his head. We can't generate gravitational waves with current technology. It takes colliding black holes or neutron stars. The energy scales are impossible. But we can manipulate space-time in other ways. You argue. What about using a particle accelerator, CERN or Fermilab, when we collide high-energy particles? We're creating tiny regions of extreme space-time curvature. It's not a gravitational wave, but it's gravitational manipulation. Maybe that's enough. There's a long pause. Then Hayes says, I'm going to need you both to write this up. Full analysis, full recommendation, within 2 hours. The Security Council needs to see every option we have. This is the most important decision humanity's made in, well, ever. We need to get it right. The call ends. Michael and you look at each other. We're really doing this, he says. We're planning first contact. We're planning a response to first contact. You correct. The contact already happened. At 2:51 a.m. on November 12th, when that magnetic signal washed over Earth, We just didn't realise it until now. Michael starts typing. Okay, 2 hours to save the world, no pressure. But as you start writing, one thought keeps nagging at you. The Trinity signature arrived in 3 stages, 19 and 37 minutes apart. 3 signals, 2 intervals, 19 and 37 are both prime numbers, and their sum 56. You have 32 hours left before 3/Atlas exits range. 32 plus 56 equals 88. Another mathematically significant number, 88, is the number of keys on a piano, the number of constellations in the sky, and in Chinese culture, a symbol of fortune and good luck. Coincidence, maybe. But after the Trinity signature, you're not sure you believe in coincidences anymore.